today's seminar. The speaker is Professor David Watts from the University of Manchester. Let me tell you a little bit about David's background. He graduated in chemistry and physics for the University of Wales and completed a PhD, and was then appointed after a few other positions to the University of Manchester, where he has a lectureship in biomaterial science in, wait for it, in the School of Dentistry. Right? Some of you might find that a little bit of a surprise. He appointed to a lectureship there and has risen to the ranks of professor. He's given a personal chair in 2000. He also coordinates there, I think it was the first BSc degree course in biomedical materials. He has a number of other positions. He has an adjunct research professor in Oregon, Portland, and an honorary faculty member in the University of Padua. He's received a number of awards for his work and has been editor-in-chief of the journal Dental Materials since 1998. So he has a number of accolades as he comes to us, and he's going to talk to us today under the title of Mathematics and the Beauty of God. David, thank you.
Good afternoon, ladies and gentlemen. I'm very glad to be here, and I thank the directors for the invitation. As I say, I'm particularly glad because this is the Faraday Institute. Michael Faraday is my #1 role model in science, and my most successful ever scientific paper was published in the Transactions of the Faraday Society. Now, Faraday was not noted as a mathematician. In fact, his formal education in that respect was relatively elementary. But James Clerk Maxwell paid this tribute to him in that regard, that he was in reality a mathematician of a very high order, one from whom the mathematicians of the future may derive valuable and fertile methods. This, of course, was alluding to Faraday's field theories in electricity and magnetism. And it's appropriate that one of the sort of formulations of electromagnetic theory with an electromagnetic tensor equation is also referred to as the Faraday tensor. Well, what is my aim in this presentation? It's not to try and prove God mathematically. There are books that attempt to do that. But it is to illustrate the relevance and plausibility of Trinitarian Christian theism for the philosophy or understanding of mathematics, and to explore the relationship between mathematics and divine beauty. Now, there are lots of mathematics books written for popular audiences, such as this excellent one by David Acheson from Oxford. And there's this one here, John Adam, A Mathematical Nature Walk. There's this one here by John Polkinghorne on meaning of mathematics. I have that one here with me. And that's a much more advanced philosophical reflection by multiple authors. And then there's this book by Mario Livio, Is God a Mathematician? So why consider this subject? Well, a lot of part of university life these days are very, very utilitarian. And I think we need to some extent, resist that. I mean, by all means, let us be practical and applied as much as possible. I try to be myself. But there is a value in truth and knowledge, I believe, for its own sake. And then again, Christians have sometimes regarded mathematics as a classic area where Christian belief is irrelevant. I disagree. And as we've seen, there are cultural mathematics books which are among the best sellers. And areas like chaos theory, fractals, and so on have widened the applicability of mathematics. And in the book of Job, where God asks Job, can you count the clouds? And it's a rhetorical question. I suppose the answer is expected to be no. But fractal theory has led in some direction to, in some senses, count the clouds, and therefore, to widen the domain of application. Then again, there's the development of mathematical software, programs like Maple and Mathematica that remove a lot of drudgery from routine calculations and enhance geometrical insights. And through all this, and through the popularization of mathematics, people have been educated to imagine multiple dimensional space and parallel worlds. As for example, in Edwin Abbott's book 100 years or more ago, Flatland, where there is the idea of a two-dimensional world and what would it like to be a creature in a two-dimensional world. But equally, we can imagine multiple dimensions. And so I believe this gives some new opportunities for raising Christian perspectives. And again, there is the statement in the Westminster Shorter Catechism that man's chief end is to glorify God and to enjoy God forever. And as several people have said, we glorify God most when we enjoy God the most. And so if we can enjoy God in and through our work and our studies, then this is pleasing to God. So what is mathematics? Well, it's difficult to define, and I wouldn't presume to have a definitive definition. We can say it's exploration, discovery, invention and application of abstract patterns. Or maybe putting it more theologically, we could say it's exploring certain domains of created reality, numerical, spatial and cognate domains in the order and symmetry, variety of pattern and change. Of course, the role of logic is very important still, and so logical proof of theorems remains a vital component of mathematical practice. Now, many people have spoken about the amazing applicability of mathematics to science, and starting perhaps with Galileo there, mathematics is the language in which God has written the universe. Eugen Wigner, Nobel laureate, referred to the unreasonable effectiveness of mathematics in the natural sciences. And Heinrich Hertz, who of course in a sense was one of the first to experimentally demonstrate the relevance of Maxwell's equations of electromagnetism, said that these mathematical formulae have an independent existence and an intelligence of their own. And Steven Weinberg, particle physicist, it's positively spooky how the physicist finds the mathematician as being there before him or her. Then there is there's a very interesting book here if you want to go into that subject more deeply by Mark Steiner, who's a philosopher at the Hebrew University of Jerusalem. So he is a theist, but a theist from Judaism, and he argues that we cannot account for the applicability of mathematics on the assumptions of naturalism. But it goes into very great depth, which I've neither the time nor the competence to try and deal with right now. And we could multiply quotations from people like Richard Feynman, Roger Penrose, and in an earlier era, Johannes Kepler. And then you may well have come across this quotation before from Sir James Jeans, that we have already considered with disfavour the possibility of the universe having been planned by a biologist or an engineer. From the intrinsic evidence, the great architect of the universe now appears as a pure mathematician. And Stephen Hawking, who needs no introduction, says, why does the universe go to the bother of existing? Even if there is only one possible unified theory, it's just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? Now, about 6 years ago, I had a year living in Germany, in the city of, or small city of Jena in Thuringia, right in the very heart of Germany. And I lived on a road called Forest Way, And across the street there was this house, and I took a photograph of it because it had, it had not one but two wall plaques on the equivalent of our blue plaques of where famous people have lived. And this was of this gentleman, Gottlob Frege, who was a professor of mathematics and was, by common consent amongst philosophers of mathematics, one of the deepest thinkers who've ever engaged the topic. He preceded the efforts of Bertrand Russell and co-workers who drew upon Frege's insights. And this is something that Mark Steiner discusses in this book to which I've just referred. Now, a big issue is whether mathematics is discovery versus original invention. Where do the structures of mathematics come from? Are they merely the creation of the human mind, imposing its categories upon an intrinsically formless world, or do they have some kind of prior existence? Well, the former view, the idea that it's us imposing our categories on the world, is, of course, the outlook of Immanuel Kant, whereas the latter view, that the structures have prior existence, is traced back to Plato and his theory of forms. And this is nicely illustrated in this book on complex, or visual complex analysis, a really great textbook on that topic by Tristan Needham. He says in the preface, "My book will no doubt be flawed in many ways of which I'm not yet aware, but there is one sin that I've intentionally committed and for which I shall not repent. Many of the arguments are not rigorous, at least as they stand. This is a serious crime if one believes that our mathematical theories are merely elaborate mental constructs precariously hoisted aloft. Then rigor becomes a nerve-wracking balancing act that prevents the entire structure from crashing down. But suppose one believes, as I do, as Needham does, that our mathematical theories are attempts to capture aspects of a robust Platonic world that is not of our making. I would then contend that an initial lack of rigor is a small price if we can see more directly and pleasurably than would otherwise be possible." Now, a number of years ago now, you might have seen this film about John Forbes Nash, A Beautiful Mind. And the implication of the very title there is that mathematics is beautiful, but of course it raises the question, from when? So if you think beautiful thoughts, beautiful mathematical thoughts, but where does this all come from? Well, I understand the answer was in the lecture last time, but so what is beauty? Well, Roger Scruton has one of those very nice, a very concise introduction, very short introduction on the topic of beauty, because he was a professor of aesthetics. And so we could say, well, it's an aesthetic quality that names what we find attractive, satisfying, and excellent. With visual art, of course, we perceive that through the visual senses, with literature, by the mind and imagination. And there are various ingredients such as unity, balance, symmetry, and harmony of parts. Or not necessarily subject to those analyses. And that, I think, is the case with the biblical writers. They refer to beauty, but are not trying to dissect it like a philosopher might. But certainly in the Bible, used as a generalized positive response to someone or something, including the inner beauty of character and personality. So what do biblical writers find beautiful? Well, just a few quick examples. Crowns, a crown of beauty, garments of beauty, ornaments, voices, houses, city, elevation of a mountain. And God has made everything beautiful in its time, says the writer of Ecclesiastes. So beauty as applied to God. There's a nice book here by Patrick Sherry, a theologian, from Lancaster University, called Spirit and Beauty, published by SCM Press. And this, of course, as applied to God, is a more metaphorical usage. It implies positive qualities for identifying the perfection of God on the one hand, and also the pleasure that the believer finds in the contemplation of God and God's perfections as a spiritual response. But we can say, well, beauty does not define God. God, as the ultimate being, defines beauty. And in the Psalm 90, we read that, well, there is a prayer that the beauty of God is communicated to God's covenant people. May the beauty of the Lord rest upon us. And in line with Hebrew parallelism, in this case, not in the Psalms, but in Isaiah, there is the parallel statements in that day, the Lord of hosts will be a crown of glory and a diadem of beauty. So glory and beauty are their parallel concepts in this sense, or they're intersecting concepts. And in the New Testament, we read of the Son of God in the opening paragraph of the Epistle to the Hebrews, that Jesus is the radiance, the apogeusma of God's glory. And the beauty of God is a major theme in the Psalms and amongst certain Christian thinkers down the centuries, particularly Jonathan Edwards, the great American theologian, and the Catholic theologian Hans Urs von Balthasar, who wrote earlier in the last century. Now, beauty for Old Testament Israel in the tabernacle and temple was, next to nature, their most vivid experience of aesthetic beauty. And again, the psalmist says his request is to gaze upon the beauty of the Lord and to seek him in the temple, with the implication that the whole ambience and environment and experience of being in the temple conveys something of the beauty of God. And in this view of the sanctuary as a representation of what it must have been like in the second temple, there are various vessels and furniture items in the temple, and then the priests tending the lamp of the seven-branch candlestick, and the high priest kneeling to prostrate himself towards the inner sanctum or holy of holies. And the high priest is presented, as we read the descriptions in the Pentateuch, as beautiful in his uniform. The uniform of the high priest was itself a microcosm of the temple and reflected something of the beauty of that temple. And in particular, on the high priest wore a breastplate of 12 stones representing the 12 tribes of Israel. And of course, precious stones are normally regarded as beautiful. But this imagery suggests a link with the New Testament vision of the city of God, and maybe one link between divine beauty and mathematics. For example, if you think of the last book in the Bible, the Apocalypse, in chapter 21, we read that the holy city, having the glory of God, her light was like unto a stone most precious, as it were a jasper stone, clear as crystal. And the verse goes on. But my inference is, and this came to me during a rather boring sermon I was listening to on one occasion, that a crystal is a suitable object to illustrate divine beauty. In this case, we're looking at an X-ray diffraction pattern of a crystal which reveals the order in the crystal, although of course crystals also exhibit disorder, various point and lattice and line defects, so there is disorder as well as order in crystals, but nevertheless they are beautiful objects. And again we see that unity, balance, symmetry and harmony of parts. But of course there's now the relevant, and been for many years, the relevant branch of mathematics, namely group theory, that underlies the specific beauty or symmetry of crystals. It permits us to determine the number of possible arrangements of crystals and the types of lattice that they form in three-dimensional space. So there are 4 types of unit cells, 7 types of crystal classes, 14 Bravais lattices, and all describable by group theory. And in the 19th century, onwards, physicists and mathematicians spent a lot of time classifying change, and associated with every change there's always something that, well, something's changed, there is also an invariance or something that doesn't change. And so from one angle you can say mathematical symmetry groups have these properties. There must be the possibility of no change, in other words things standing still as it were. A reverse change, and actually a lot of this applies to rotations of objects in space. A reverse change must be possible to restore the original shape, and any two consecutive changes like click click must give a result that could equally be well obtained by another single change. So if we look at an object like a sphere, for example, this has got a very high level of symmetry, and there are a number of things that kind of approximate to spheres, but in detail have different levels of different types of symmetry, and you have incomprehensible equations like this that describe the rotational subgroups, in this case of a virus crystal, and of various 3D structures, and then objects like a dodecahedron. And that takes us back early in the history of mathematics to the Platonic solids of polyhedra constructed from regular polygons, and with a limited number of possibilities. Again, in the Pythagoreans had the idea of the harmony of the spheres, and here represented by only 5 regular convex solids that can be circumscribed by a sphere. Now, to the Pythagoreans, the pentagon was a symbol of the universe, and if we look at certain diagonals like those labelled P and Q there, and we take another line between the top and the bottom left, then there is an intersection of those other diagonals, and the point of intersection divides the pentagon into a particular fraction, which is known as the golden ratio, the golden section, the golden mean, or sometimes the divine proportion. And this golden section, symbol phi here, Greek phi, if we consider a line of length L, and still sticking with a kind of geometrical approach, if you divide it, you can divide it in such a way, at such a point, that the sublengths A and B have the relationship that phi is equal to the total length over A, which is, again, you can cut it so that it is also equal to A over B. And if you rearrange that, you get that simple equation. But you can generalize the top right equation as shown there. L over A equals L plus A over L. And if we make A equal to 1 and L we call X now, we change the name of the variable, then we have this relationship, X plus 1 over X is equal to X over 1. And you can rearrange that so you get a quadratic equation. And you can have a positive root, which is phi, and there is also a negative root. And the product of those two roots is -1. Now, this golden mean or divine proportion can also be expressed as the most irrational number, the least well approximated by rationals. And here in this equation, we've got a kind of recursive or fractal definition that phi is equal to 1 over 1 plus x, where x itself is equal to 1 over 1 plus x. And so that makes the number phi to be the most irrational number. Now, there are lots of unexpected encounters with the golden mean. For example, if we have a sequence of integers formed by summing the preceding 2 integers, for example, if we look at number 4 here, that's a sum of 1 and 3. If we look at 7, it's a sum of 3 and 4, and so on. And there's another example there. And if we take the ratio of 2 consecutive terms, like 18 over 11 or 45 over 28, in the limit where the number of terms gets large, towards infinity, again this comes out to be 1.618, etc., or phi, the golden mean. So this is a totally unexpected occurrence or appearance of phi, this time in a non-geometrical context. So that means that whatever we're doing here about series and in geometry, there is a sort of hidden connection between them. And the simplest of these kind of sequences, of course, the Fibonacci series, 0, 1, 1, 2, 3, 5, 8, etc., etc. And of course, this has an equation involving phi, and this appears and pops up again and again in shells, in sometimes in thunderstorms and in distant galaxies. So the mathematically they have this underlying connection to the divine proportion. Now, the ingredients of mathematical beauty and pleasure are also applicable to music, and for a start, there is an alternation of tension and relief. You're sweating away in your GCE mathematics class or your advanced third year pure mathematics degree course, and you're perplexed. And then the penny drops and you're illuminated. And again, sometimes there's a more relaxed experience of a realization of expectation. Again, surprise at the unexpected, like we've just tried to illustrate, and the perception of unexpected relationships and the enjoyment of patterns. And in famous equations like Fermat's last theorem, kind of brevity is the soul of wit. It's a very simple equation, and yet how much effort and ingenuity has been expended in trying to prove it. And with music, of course, even simple musical intervals can stimulate an emotional response in somebody with no musical training whatsoever. And so this is just even the tip of the iceberg in relation to mathematics. Now, how about the distribution of mathematical gifts? Well, this is one area particularly where these gifts have been widely distributed among the peoples of the earth. And sometimes science is greatly dependent upon having equipment and libraries and so on and so forth. And Islamic, Jewish and Christian mathematicians have made many significant contributions. But just looking at some of the Christian mathematicians of the 16th and 19th centuries, there are some famous names here who've made massive contributions. The photo is of Leonhard Euler, and his formula is, of course, one of the most beautiful in mathematics. Whenever there is a poll about beauty in mathematics, this comes out as the top equation, because in a way it's so simple. It connects 5 fundamental constants of mathematics, namely the exponent e, pi, I, the square root of -1, and of course 0 and 1. So it includes the most important mathematical operations of addition, multiplication, and exponentiation, and it includes the constants symbolizing the different branches of mathematics, like arithmetic, algebra, geometry, and analysis. And E, of course, this is an extremely useful equation in physics and in many areas of natural science. And according to Einstein, it's the greatest mathematical discovery of all time. In the complex numbers, where you have a complex plane of positive to negative, and then in the vertical axis, the square root of -1 and the negative of that, minus I, if you do integrate in a contour, then this is an equation that pops up. And Fritz Schaefer has said, referring to this, I remember when I learnt as a senior at MIT, the result of the contour integration was 2 pi I times the sum of the residuals. He says, for me, this was as about as close to a revelation as I had received up to that time in my life. So, yeah, sometimes after long derivations and stuff, you're in a lecture, you're studying and taught, the final result, and sometimes it's quite stunning in its unexpectedness and relative simplicity. Now, again, generalizing ultimately Pythagoras, Bernard Riemann, who another Christian mathematician whose developments were utilized by Albert Einstein in relativity, describe this Riemann curvature tensor of four-dimensional space-time, so there where time and space put on an equal footing. Now, there's lots of theories in physics where the beauty is associated with symmetry. And this book here, for example, by Vincent Icke, published by Cambridge University Press, The Force of Symmetry, when you think about it, normally we think of forces in a very sort of mechanical way, and we don't think of forces in terms of a symmetry or a symmetry group. But there are areas, particularly in particle physics, which the symmetry is really the key to understanding the coherence of the fundamental particles. And then again, this lady, Emmy Noether, derived this equation about relating symmetry and conservation laws. A broken symmetry should produce a broken conservation law. There's a famous story about her that she was at the University of Göttingen, and the boss there was David Hilbert, and he wanted to have Emmy Noether brought onto the faculty. And the faculty were very resistant to this because of her gender. And he said, "Gentlemen, this is a university, not a bathing club." So then Werner Heisenberg was, of course, one of the developers of quantum theory in the 20th century, particularly in the form known as matrix mechanics. And he had generally a rather materialistic outlook. He wasn't, the very best of my knowledge, anything like a Christian believer, unlike people like Planck, for instance. But he said, "I had the feeling that looking through the surface of atomic phenomena, I was looking at a strangely beautiful interior, and felt almost giddy at the thought that I now had to probe this wealth of mathematical structures nature had so generously spread out before me." If nature leads to mathematical forms of great simplicity and beauty, we cannot help thinking that they reveal genuine features of beauty. Now, most complicated equation, then we get back to the Dirac equation, again formulated here in Cambridge, of combining relativity and special relativity and quantum mechanics, time-dependent quantum mechanics. And Paul Dirac had to wrestle with trying to make his equation self-consistent, and he devised these matrices that we see in the lower part, rotation matrices for 4 space and time coordinates. And it can be put in an equivalent form up there. But despite his militant atheism, he used beauty as a criterion for developing mathematical truth. And of course, in doing that particular equation, he predicted the anti-electron, which in a way it's a bit like in a quadratic equation where you have your positive root and a negative root, where the one may be physical, have a physical significance, the negative root may appear to have no physical significance, but he kind of made the mental jump of saying, well, maybe this does have physical significance, and it has the properties of what now we call the anti-electron or the positron, and led to which led others to its discovery. So Michael Atiyah, again another Cambridge figure and former Manchester Grammar School pupil, developed an index theory in which was said to open up tunnels between areas of mathematics that did not previously appear to be related. It was like archaeologists discovering the same characteristic patterns in tombs from two seemingly unrelated cultures. And in areas like that, for example, in the development of geometrical algebra, there is, just like with the increasing unity in physics, with the various laws seem to be combining and going towards grand unification. So also in mathematics, various streams of thought, sometimes disparate areas, are knitted together into a beautiful integrated scheme, in this case of geometrical algebra and calculus. Now, if we turn to the topic of Plato's mathematical realism, we can say, well, Platonism and Christianity are quite distinct. But it's possible with many ideas of extra Christian ideas or non-Christian ideas to detach them and purge them from their original context. And when that is done, they may turn out to be congruent with Christian belief. So we could acknowledge some logical and or temporal pre-existence of mathematical forms before they become embodied in the actual rhythm and functioning of the physical universe. And as Christians, thinkers about this issue, we could say, well, the place where these forms or mathematical existence resides is in the eternal mind of God. And therefore, we can discover them. So we can think God's thoughts after him, as Kepler suggested. And so even in the most abstract branches of mathematics, like ideas of multi-dimensional space, 10 or 11-dimensional space, these have a part of free creation by the human mind, but I would put it to you that this may be perhaps a relatively originated by human beings, but more absolutely they are relative to God's contemplation of all possible worlds, from which God has chosen the contingent worlds that do have existence. So going back to the original question of, is mathematics, is it a construction of our minds, or are we discovering things out there for us to, the truth is out there, as the TV show said. But actually the two things are not so necessarily in conflict, because human beings are, in the Christian understanding, made in the image of God, and so things that we think we are creating, mathematical structure. In fact, we are only enabled to do that because we are made in God's image, and we have given insights. So I'd like to draw things to a conclusion with some theological observations. Again, in the book of Ecclesiastes, we read that about a restless desire for beauty. God has set eternity in our hearts, and we have a kind of, intrinsically as human beings, we have a kind of quest for this. But the world itself can never completely satisfy that. And how do we account for that? Well, in the Christian understanding from the New Testament, there is a tension between what is disclosed to us already in Christ and what is not yet. There is a future consummation. So there is a present and a partial enjoyment of divine beauty which is accessible to us now, if we only open our eyes and look for it and perceive it, which shall be wonderfully consummated hereafter in the life everlasting. So, because therefore our understanding is provisional and partial, humility and openness to new ideas is a prerequisite for Christian scholars. As the Apostle Paul said, "For now we see in a mirror dimly, but then face to face." He contrasts the already with the not yet. Now, already, I know in part, then I shall know fully, even as I have been fully known. Freeman Dyson, great theoretical physicist, said this, that Western science grew out of Christian theology. It's probably not an accident that modern science grew explosively in Christian Europe and left the rest of the world behind. 1,000 years of theological thinking nurtured the habit of analytical thinking that could be applied to the analysis of natural phenomena. So maybe deciding how many angels could dance on the tip of a pin was not altogether wasted, because it nurtured that habit of analytical thinking that we could apply in our day and later to other things. So it's possible to enjoy mathematics now as a good gift of God that clearly manifests the divine beauty, but if that enjoyment is not coupled with genuine love of God as the giver, then really we are in danger of idolatry and ultimate frustration. There are well-known stories about certain mathematicians who were literally obsessed with mathematics, and maybe their own lives, their personal lives, and even their care for their bodies and so on, suffered as a result of their obsession with mathematics. And Paul's critique of pagan society is, although they knew God, they did not honour him as God or give thanks to him, but became futile in their thinking. By contrast, again in the Apocalypse of John, the vision of the ultimate future, of God's final, definitive purposes, express the incorporation of all that is good in human culture, and we can include mathematics in that, that by the light of the city of God, the nations will walk and the kings of the earth will bring their glory into it. That's not saying that they'll bring God's glory into it. God's glory is already there. But it's a mystery and paradox of the fact that God's glory is kind of additive, or you can add to God's glory, from glory into glory. So, there we are. But as maybe William Blake said finally, to see world in a grain of sand and heaven in a wild flower, hold infinity in the palm of our hand and eternity in an hour. Thank you for your attention.
Thank you very much. It's fascinating. I'm sure that set our minds thinking about beauty and mathematics and lots of questions. So over to you. Who would like to be first? Rodney, hand up at the front, and then I can see one there, and I see another one at the back.
Well, thank you very much, David. That was a brilliant talk. Absolutely loved every minute of it. But going back to the beauty of God, would you like to comment on the fact that, of course, the Hebrews were forbidden from making images of God? I mean, the temple is beautiful, the garments of the priest and so on.
Yeah.
So would you just like to comment on?
I regard, when the New Testament, in the era of the New Testament, created by the coming of Jesus, Jesus himself is, of course, the ultimate image of God. So you might say, well, God broke his own rule. But so maybe the original prohibition was against upstaging the incarnation of the Son of God. But maybe a lot more could be said by others.
Yes, I've got one hand just over there. We'll be patient, the microphone will come. Yes, just there.
Oh. Thank you. I wish I were more numerate, and then I would have got a lot more out of your fascinating talk. From the side of a more linguistic and theological angle, something that interests me is the the title of Christ, which we translate word, the logos,
Yeah.
of course also means ratio.
Yes.
We are, in that we are in God's image, we are rational, again
Yeah.
connected with ratio as well as
Yeah.
reason, and connected with this idea of God as word. So the whole idea of God writing the universe in the language of mathematics, and mathematics as a sort of insight into the mind of God, is already deeply entrenched in this whole idea of God and of Christ as the Logos.
Yes, indeed. Yes, thank you very much. Yes, I totally agree. That's a very helpful comment. Thank you.
Any other hands that I can see? Yes, there's one over here. Please raise your hands high so that I can spot you easily. Thank you.
Thank you. If I may ask a question which possibly you nor no one can answer. You clearly alluded to the point that you think of mathematics as a discovery.
Yeah.
And you also alluded that you think that mathematics is created by God. But I might suggest that, and here's my question, is mathematics something that just is, or was mathematics actually created?
Well, it's more what I personally think of is it's more like the kind of structures of mathematics, if I can use that expression loosely without being pressed on a very hard definition, that are discoverable. I mean, particular forms of things, like, for example, a matrix table or something. Well, you know, I can quite understand that as, you know, that we create that, but then, you know, but then again, we're able to create things like that because we are in the image of God, and because we, you know, as the previous questioner just said, you know, we've been given rational minds. But I think there are things out there that are discovered. So, you know, I find it difficult to imagine a world that is, shall we say, amathematical in its inherent inner essence. I mean, that's part of my difficulty with Immanuel Kant's philosophy, that one, according to him, one can never know the thing in itself, but one can only kind of deal with phenomena or kind of more perceptible qualities. So I'm not sure I'm fully answering your question, but you've hit the nail on the head with the nub of the question, really. And I suppose ultimately it must be partly a mystery. So I wouldn't want to eliminate mystery by rational analysis when things are beyond our ken, really, in some ways.
There's a hand here.
Hello. As a pure mathematician,
Yeah.
I take it from a complete different angle.
Right, yep.
And that mathematics is a pursuit of truth and meaning.
Yeah.
And that those two things have also a relationship with the outside world, so with reality ontologically distinct from our mind, is God's will or an accident, depending if you are a theist or not. But one can do mathematics outside of the nature of the world.
Yes,
if it makes
yes.
sense.
One can imagine possible worlds that may not actually exist. So as a manifestation of our imagination, yeah.
And that in itself is a reflection of the divine logos.
Yeah.
Because the divine logos transcends the reality that we can see with our senses. There is a reality that is outside the material.
Yeah.
If it makes sense.
Yeah.
And so mathematics, in that uniqueness of having both aspects, bridges the two worlds.
Yeah, that's very well put. I wouldn't want to be kind of reductionistic and too much either or on the question.
So does the fact that we can imagine a mathematical world mean that it necessarily has to exist?
Only in the sense that I believe it exists in God's contemplation of all possible worlds. So God can envisage, in other words, what I think is, maybe wrong, but I don't imagine even in our wildest mathematical dreaming and speculating that we are one step ahead of God. That He's always one step ahead of us. But in terms of whether things fit or apply to the world, obviously there are many areas of mathematics that were developed purely in pure mathematics, and then they turn out to be useful in applied mathematics, such as matrices and groups and things like that.
There's one down the front here.
Thank you very much. Thank you very much. One of the things I find most astounding as a physicist is that if you take all of our current physics appreciation of how the world works, and you stick all the numbers in, the universe only works if all of the physical constants are exactly what the physical constants are. You only have to change any of them a smidgen, and the world no longer works.
Yeah.
I find that is
there's a
spooky,
yeah.
very, very fascinating. And I can also recall there's some solutions of the wave equation where it works perfectly as the series diminishes, and if you chop it off at the right point, gives you the right answer. Mathematically, however, if you continue the series, it gets bigger again.
Right.
So something funny going on there,
Yeah.
but thank you very much indeed.
Thank you.
We wouldn't be here.
Yes, that's right. We're here because it works.
I think you've exhausted our mathematical minds, David. I think at that stage we will draw things. It's a question over there. I was going to draw things to a close, but I'm seeing another question.
I think when I always think about this, I always come to Wittgenstein and his comment about there's a
Sorry,
point.
can you?
I always come to Wittgenstein's idea that when he thought about this, that there's a point which we should no longer speak. And I always feel in a lot of these discussions, without criticising your talk, a lot of this material, that's where Wittgenstein would say you should stop. Do you agree with that? Or?
I'm not sure I fully grasped the question, to be honest. Maybe in my hearing.
Sorry,
so Wittgenstein?
Yeah,
said?
Wittgenstein said that there was as you go into philosophy, there's a point at which we should stop talking about these topics because you can't give a clear answer. It sort of gets too much into metaphysics, if you like.
Philosophy as in every other area of human endeavour. Yeah.
At that point, I think I'll draw things to a close. David, you stretched our minds. There's a mathematical equation for stretching minds, I'm sure. And it's been a fascinating and lovely talk. Thank you ever so much.
Thank you.
Thank you.